Hey guys, welcome back to my channel. So in the today's video we are going to discuss the approximate analysis of BJT amplifier, and in the previous video I have discussed the exact analysis of BJT amplifier, which are just used for derivation purposes, and for the numerical purpose you must be knowing this approximate analysis of BJT amplifier, right? So generally to solve the numericals we use this approximate method. Okay, so generally what happens in approximate analysis, the BJT is replaced with approximate common emitter HParameter model, which is obtained by neglecting the parameter HRE. Yes, let me show you first. So guys, here you can see the exact common emitter model, and this is the approximate CE model. So the thing is, we have to neglect the value of HRE. The HRE value is very small, and we just have to approximate the value of HRE, which is equals to 0. Okay, so our circuit get reduced to this form. Now all BJT amplifiers are analyzed by using only common emitter configuration or common emitter model in approximate analysis, right? And the approximate analysis becomes valid only when the HOA into my RL dash should be less than equals to 0.1. Then only we can do approximate analysis. Okay, so guys, this is the common emitter amplifier. Okay, and we also call this amplifier as RC coupled amplifier. So you must be aware of the term common emitter. The first thing is that the common emitter means the emitter is grounded and the input is provided by the base terminal at the base terminal, and the output is collected at collector terminal, right? Why this amplifier is called RC coupled amplifier? So you must be knowing that here the load is a resistor. So in RC coupled amplifier, if the load is a resistor and a capacitor is used to connect the amplifier and the load, then this type of arrangement and this type of circuit is called RC coupled amplifier. Okay, so here let's analyze this circuit and see what the circuit tells about it. Okay, so here in this circuit we have used the self-wise configuration, right? This is a self-wise configuration, and this configuration is used to maintain the operating point. Okay, you must be knowing this fact that self-wise configuration is used to maintain the operating point stable, and hence our collector current will also become stable. Okay, now next is emitter bypass capacitor, which is CE capacitor, is connected to prevent the decrease in the voltage gain. Why? Because if CE is not connected, then the resistor RE will reduce the voltage gain. Okay, now the blocking capacitors and the coupling capacitors are connected to provide the DC isolation to the biasing circuit. If CC is not present, then the load RL will drop DC current and it will disturb the operating point. Okay, and similarly if CB is not present, then VS and RS can disturb the operating point. So the CB, CC and CE are generally the large capacitors, generally in microfarad, because they should offer negligible reactance at the frequency of the AC input signal. And the shunt capacitor here, this is a shunt capacitor, is connected to control the bandwidth of the amplifier. Okay, you must be knowing this fact that the bandwidth is inversely proportional to the shunt capacitor. The shunt capacitor is a small capacitor, generally in picofarad, because it should offer a high reactance at the frequency of AC signal. Okay, so guys, this is all about RC coupled amplifier, and the common emitter amplifier is generally called the RC coupled amplifier. Okay, now we will discuss the procedure to analyze the amplifier and discuss the amplifiers at medium frequency, low frequency, as well as at high frequency. Okay, so let's get started. So guys, the step 1 says identify the BJT configuration in the given circuit. It means that you have to analyze BJT is operating in which configuration, right? Whether it is CC, CB or CE. Okay, step 2 says Draw the medium frequency AC equivalent circuit by replacing the large capacitor with short circuit. Guys, the large capacitors are generally the blocking capacitor, coupling capacitor and bypass capacitor, right? And the small capacitor with open circuit. The small capacitor is generally the shunt capacitor, which is connected in parallel with the load resistor, okay? And also by connecting VCC node to the ground. Guys, we have studied that in small signal AC analysis we generally disable the DC supply, okay? So here we are also doing the same thing. Now the step 3 says replace BJT with approximate small signal model and calculate the desired values. So these 3 steps majorly help you in analyzing the BJT as well as doing the numerical parts, okay? So guys, let's first understand medium frequency AC equivalent circuit. Here you can see that I have the RC coupled amplifier, and first we do the analysis of common emitter amplifier, that is this RC coupled amplifier, okay? So according to step 1, we have to identify the type of configuration in the BJT. So here you can easily see that this configuration is common emitter. As we know that this is the emitter and the emitter is grounded and the input is connected to the base and the output is connected to the collector region, okay? So we are done with the configuration. So let's move on to step 2. According to step 2, draw the medium frequency equivalent circuit by replacing the large capacitor with short circuit. Okay, we have to replace the large capacitor with short circuit. I have mentioned earlier the large capacitors are blocking capacitor, coupling capacitor and bypass capacitor. So we just have to short these 3 capacitors, right? Now our next step is small capacitor with open circuit, and we know that the small capacitor is basically the shunt capacitor and we have to make it open circuit, okay? And the DC supply is disabled in small signal AC analysis, so we have to disable the DC supply. So this is our DC supply and I have to disable this DC supply. That means I have to ground this DC supply, okay? So I have disabled the DC supply. Now guys, let me redraw the following circuit. So guys, this is the circuit, okay? And here you can see that the RB is basically R1 parallel to R2, which we have done earlier also. And now we have to develop the HParameter model of this circuit. Now it's very easy. From the earlier video you know that how to convert this circuit into HParameter model. So let me just convert it. So this is the HParameter model of the required circuit. Now here you can see that I have taken only the approximate circuit, guys. I have neglected the HRE. So this is my approximate model of HParameter, right? And now I will do all the analysis based on this model, and you will find this analysis very, very easy, as well as this analysis is used in numericals. So you must be clear with the concepts. Okay, so let's start. First, I will mark the input as well as the output voltage. So this is the input voltage, internal input voltage, right? And here I am getting the output voltage, guys. Okay, now first we have to calculate the current gain. Guys, the current gain is given by, as we all know, that it is the load current upon my input current, and at the input I am having the base current. So let me mark these current values first. The load current is flowing in this direction, okay? Yeah, and base current is flowing in this direction and also here, right? Now applying the current divider at the output circuit. Guys, this is similar which we have done in the exact analysis, okay? So let me just do it very fast for you. it is minus HFE IB into me 1 upon me HOE upon me 1 upon me HOE plus me RL dash. Okay, now IL upon me IB, taking this term here, we are getting minus HFE upon me HOE, taking the LCM 1 plus me RL dash HOE upon me HOE, minus HFE upon me 1 upon me HOE RL dash. So guys, this is the general formula for our current gain. Okay, so the current gain is given by minus HFE upon me 1 plus HOE RL dash. Okay, so generally if HOE RL dash less than 0.1, then the current gain approximately equals to minus HFE. So guys, this is the approximate analysis which we are looking for. Okay, so negative sign appears because load current RL and output current IC are in opposite directions. That's why we have taken this negative sign. Okay, now second thing, we have to calculate the input resistance. The input resistance is given by input voltage upon my input current. The input voltage I have marked here, it is VI, and the input current is the base current. And from the input circuit, we this VI is equals to HIE into my IB. Okay, so just replacing this VI with HIE into my IB upon my IB, and from here input resistance will be equal to HIE, right? Very simple formula, highly used in numericals. Okay, and the net input impedance, guys, this is the internal input impedance, and the net input impedance is the, which I am taking RA dash, is a parallel combination of RB into my HIE, as this thing you can see from here. Okay, from here I am getting, this is the input resistance, and when input resistance it is in parallel with RB, so this is the net input resistance. Okay, now next thing is a voltage gain. The voltage gain is given by output voltage to input voltage. Okay, so the output voltage here is, so guys, let's just take the parallel combination of this, and after doing the parallel combination of this, I'm taking it RL double dash, and it is a parallel combination of 1 upon my HOE parallel to RL dash. Okay, so here, from here, the output voltage is given by minus HFE into my IB, this into my RL dash, right? Because we have just taken the equivalent circuit here. Okay, so this is our output voltage, and the input voltage is given by which we have taken earlier, and this input voltage is HIE into my IB. Okay, so voltage gain becomes minus HFE IB into my RL dash double dash upon my IB into my HIE. Okay, so from here we can cancel out the IB terms, and voltage gain is given by minus HFE RL double dash upon my HIE. Okay, and we have calculated this voltage gain earlier in our exact analysis. Okay guys, if HOE is approximately equals to 0, generally in numericals we are having this term approximately 0, so in that case our RL double dash will become RL dash, and in that case the voltage gain will be minus HFE RL dash upon my HIE, and this negative sign indicates a phase shift of 180 degree between input and output voltage waveforms. Okay, so you must be clear with this sign as well. Okay, so our last parameter, which is output resistance. So guys, in my previous video I have explained each and every step to calculate the output resistance, and here also I have written the steps, which is first of all we have to disable the Vs, and then we have to disconnect the RL dash, which is the load resistance, and at last we have to apply a voltage source Vx at the output port. So let me just draw the circuit diagram again after disabling and disconnecting all these terms and also applying the Vx in my circuit. Okay, so this is the circuit diagram. Guys, if you don't know how I have drawn this circuit, please visit my previous video. I have explained each and every step to draw this type of circuit diagram. Okay, so guys, let me just take these resistances in parallel, and Rs dash equals to Rs parallel to Rb. Let me just taking some notations. Okay, now applying the KVL in the input loop. Okay, we have to apply KVL in the input loop, and it will become IB into my Rs dash. Here the current flowing is IB into my Rs dash plus my HIE into my IB is equals to 0. Okay, since no voltage source is connected at the input node because we have disabled, so IB is 0. Now we have to apply the KCL at node C. Okay, let me just mark the node C. This is a node C, and just apply the KCL here. So from here Ix is equals to HFE into my IB plus my H0 into my Vx. Okay, here the voltage is Vx, and we have taken this H0 HOE. Okay, so from here IB is 0, so Ix will become 0 plus my HOE into my Vx, and Vx by Ix, just rearranging the terms, I'm getting 1 upon my HOE, and this V by I is nothing but output resistance, which is equals to 1 upon my HOE. Okay, so this is a formula for output resistance. So guys, that's all for common emitter amplifier, and we have done the analysis of common emitter amplifier. Okay, so that's all for today's video, and in the next video I am going to discuss the approximate analysis of common emitter amplifier without bypass capacitor, as well as common collector and common base amplifiers too. Okay, so till then, bye bye.